Okay. Good morning, everyone. My name's Therese O'Dwyer and I'm from RDA Sydney. I'm the Executive Officer. Firstly, I just want to acknowledge the traditional custodians of the lands on, or the many lands on which we meet today, and pay my respect to elders past, present and emerging. RDA Sydney is part of a national network of organisations that receive funding from the federal government to support economic growth in their regions. So you might really ask the question, why are we partnering in this particular project? RDA Sydney sees that to have economic growth, or you need a sustainable environment and you need a sense of livability in where you live and operate as a business. So it's extremely important that we look at the sustainability issues and promote programs or technologies that actually allow councils to engage in activities that reduce or aim to go towards net zero emissions. So although you might go, it's not an economic development activity, really, in fact, it's very much the core of economic development. Today, I'd like to thank our webinar partners, and that is Tanya from Local Government Procurement and Jared, who is from A2EP. It's been a great opportunity to partner with both of these organisations, where Jared has lined up some excellent speakers today, and Tanya has reached out to her network in such a way. It's been great. Our moderator today is Kylie Hargreaves, and Kylie happens to be on the RDA committee, but is also the chair of A2EP. Kylie has had 25 years of working history in both the federal and state governments, including stints overseas over a 10-year span. She has also been Deputy Secretary in the state government in the trade, but also in the resources side of things. So she's a great person to be moderating this discussion today. So what will happen is that we will record this webinar. We will also provide you with the slide decks that people will be using, our presenters will be using, and we'll also address any unanswered questions that you may have that we didn't have time to address. We'll also provide the contact details of both Tanya and Jared, just in case you want to follow up on some of the content today. So with that being said, I might hand it over to Kylie to start the discussion. Thank you, Kylie.
Thanks so much, Therese. Before we start today, I'd like to pay my respects to the traditional owners of the land on which we meet. We're all from different areas, but I'm in on Gadigal land of the Eora Nation, and pay my respects to elders past and present. Welcome to today's webinar on how to optimise energy use in aquatic centres. As Therese mentioned, it's co-hosted by Regional Development Australia, Sydney, the Australian Alliance for Energy Productivity and Local Government Procurement. You've heard from Therese about the RDA, so I'll just touch briefly on A2EP, otherwise known as the Australian Alliance for Energy Productivity. We are a not-for-profit organisation whose key purpose in life is to help businesses grow and do more while using less energy, lowering their costs and lowering their emissions, which is perfect for today's webinar. Aquatic centres are a key feature of almost every city and town in Australia. They provide a great service to our communities, a much loved place for exercise, relaxation, rehabilitation, social connection, and so much more. But I was a little shocked to hear about how energy intensive they actually are. Some RMIT estimates say that they can consume up to 7 times more energy per square metre than commercial buildings. So if you think about it, if you've got one aquatic centre, you're running 7 commercial buildings. So that should focus everyone's attention a bit. As councils, as much as anyone else, struggle to pay ever-increasing gas bills to heat and cool their aquatic centres, pressure is obviously building to try and find cheaper and less carbon-intensive ways to keep these vital community facilities open. To help us take a look at the ways that we can do this, we have a wonderful lineup of experts with us today. Therese has basically explained how today will run, but I will, the first 40 minutes will essentially be made up of presentations from our 3 key guest speakers. I'll briefly introduce each speaker and they can work out how to get control of the screen. So this means I'd be grateful if you could all hold your questions until the panel discussion, which I'll commence just before or on 11 a.m. And then before we close off the session, I'll ask Tanya Lawler from Local Government Procurement to provide some closing remarks. I think you've all been excellent and put yourself on mute. Please keep it that way while the speakers are speaking. Please feel free to jot down your questions in the Q&A button, which you'll see at the bottom of your screen, and we'll try and get to as many of those as possible. Alternatively, to be a little bit more engaging, if you like at the time, if you want to unmute yourself when we open up the panel discussion and ask the question directly, please do so. We'll get around to everybody. But with that, if I could please introduce our first speaker, Alan Pears, AM. Alan is a Senior Industry Fellow at RMIT University and a Fellow at the University of Melbourne's Climate and Energy College. Alan has worked in the clean energy and energy efficiency sectors for many decades, including for internationally recognised organisations like Beyond Zero Emissions. He regularly provides advice on energy policies and programs to governments, educational and community groups, as well as specific project advice to businesses and media. Welcome, Alan.
Thanks very much. And good morning, everyone. My talk is really intended to cover the basics of heat pumps and then how they might be applied to aquatic centres. At least that's the theory. Okay, let's start off with a diagram of how a heat pump works. And what we might do is start down in the bottom left-hand corner where you can see we have a cold liquid refrigerant in a pipe. And that refrigerant will then flow into a thing called the evaporator, which is just a heat exchanger like a car radiator or something like that. And that's the point where it can absorb heat from other sources around it. So that could be the ambient air, or it could be a lake, or it could be waste heat from an industrial process, or lots of different things. So what happens in the evaporator, surprise, surprise, is that the liquid refrigerant evaporates and becomes a gas. And an example of that in everyday life, if you think of a puddle of water, as the sun heats it up, the water evaporates and becomes a low pressure gas that just blends into the atmosphere. That's really the process that's going on in the evaporator. So if we're up at the top left-hand side, then we now have a low pressure gas in our pipe, and we now use an electric motor to drive a pump which compresses the low pressure gas and converts it into a hot high pressure gas. And again, if you want an example of this, if you've ever pumped up a bike tire and you've got your hand around the bottom end of the bike pump, you'll find it get pretty hot. And so that's what's happening with this compressor. The electric motor is running a pump compressing this low pressure gas, which is just like the air that we've got. But as it compresses it, it's now becoming hot. The hot gas is now kind of useful to have because it's hot, unlike what it was when it started. And so that's where now this hot gas can transfer heat, again, through a car radiator or a hydronic heating panel type thing or whatever you like. It can transfer heat to something that's cooler than it. So that's where it's providing the useful heat. And as that occurs, the hot gas condenses and becomes a hot liquid. And so again, this is where the concept of what we call latent heat is very important. So it takes a lot of energy, first of all, to evaporate a liquid into a gas, which is why boiling a kettle takes a while. But then once you've got that gas, when you condense that gas, a lot of heat is released as it changes from being a gas to being a liquid. And that's what's happening in here. And again, that's why this bit's called the condenser, because the gas is condensing. Now we have a liquid that's still at high pressure because it's connected to that high pressure section of the pipe. So then what we have is we have an expansion device or a valve, a bit like a spray can. And as that allows the liquid to flow through, the pressure is released, and in the opposite way that when we were compressing the gas, we were heating it up. As we lower the pressure, we're cooling down the liquid until it's colder than the environment, and then we're ready to start again. So that's the cycle that we're going through with this, with a heat pump. And you can see that a heat pump is very different from, say, a gas boiler where you're burning a fuel to produce heat. What we're doing is we are extracting heat energy from one place, we're concentrating it and raising its temperature, and then dumping that heat somewhere else. Now, an important thing to keep in mind about the laws of thermodynamics is that they operate from a very different temperature base from what most of us think about in everyday life. So a gas or a substance has zero thermal energy at minus 273 degrees, or what's called 0 degrees Kelvin or 0 degrees absolute. That is pretty much the temperature of outer space. And as you know, the Earth is a lot warmer than outer space. So in that sense, you can see that even air at, say, minus 20 degrees Celsius, which we think of as very cold, is actually 253 degrees Kelvin, which means it's actually quite hot, and it's got a lot of heat energy in it. And so this is why a heat pump can operate at a whole range of temperatures. And as an example, if you have a freezer compartment in your fridge, what's happening is if you put food in the freezer compartment, sorry, if you put food in the freezer compartment, it's sitting there at minus 20 degrees, and the heat pump is extracting heat from that cold food and from the heat that's flowing in through the cabinet, and then concentrating its temperature up above room temperature, and the outside of the fridge gets hot, or there's coils that get hot, which can dump that heat into your kitchen. So we all live with an example of a heat pump that is operating at minus 20 degrees. So the people who tell you heat pumps don't work in cold weather clearly haven't thought too much about their fridge. Now, how can a heat pump operate in an aquatic centre? Well, again, the first thing to ask ourselves here is what sources of heat might the heat pump have available to it? Well, the one I've got in bold is actually potentially the biggest source, which is that there is a lot of hot, humid air being exhausted from an aquatic centre. And if you can capture that energy and condense the water vapour that's in that air, you can capture a lot of useful energy, which can then be heated by the compressor and fed back into the pool. Also, the heat pump can simply draw heat from the ambient environment. So, for example, a home air conditioner extracts heat from the air and then heats that up if it's being used to heat our home. You can draw it from a lake, or from the ground itself, or from a tank of stored hot water. So there's lots of things. And also, one of the bonus things about a heat pump is that if your pool hall or other rooms within the building need cooling, then in fact you can extract that heat from them and feed that into your heat pump so that you are getting effectively free cooling because it's providing you with a heat source. If we look at the uses that it can be applied to, well, basically we've got useful heat now. So we can use it to heat the pool, we can heat the water for the showers and things, we can heat a building, or we could heat a tank of water or something like that to make that heat available at other times. So they're the kinds of key opportunities for a heat pump. Now, again, when we talk about energy efficiency, most equipment we think can be no more than 100% efficient. But as I said, the heat pump is actually not creating heat. It's extracting heat from one place and concentrating it and shifting it. So a heat pump can be 200 to even 1,000% efficient. And the language the heat pump people use is not efficiencies. Usually it's called the coefficient of performance or the energy efficiency ratio. And that is basically where if it's 200% efficient, that means it has a coefficient of performance of 2, which means you're getting 2 units of useful energy for each 1 unit of electricity. Now, heat pumps in pool centres will operate much more efficiently than that in general. Okay, just to try and give you a sense of the sort of everyday context of this, the graph down the bottom here shows what the energy content of really humid air is as the temperature increases. And so what happens is the air itself warms up and holds more heat, but importantly, as air heats up, it can hold more and more water vapor. And so as it gets hotter, if it is humid, it can hold more and more energy in terms of the water vapor. And what this means, for instance, if you're in the tropics, you know, it's a really hot, humid day and you get a change, suddenly a lot of water falls out of the sky. That's highlighting the idea of the hotter the air is, the more water vapor it can hold. And so therefore, when we're looking at this exhaust air coming out of the pool, in many cases, it's not used very effectively. It may just be pumped out of the building, or you may try to recover some heat with a heat exchanger. But a heat pump can condense the water vapor that's in that air and extract a large amount of energy while it cools the air and condenses the water. And an everyday example of this is what we call the heat pump clothes dryer, where the heat pump clothes dryer basically is pretty much a closed system. You heat the clothes to evaporate the water, and the water is then carried away in hot, humid air, and the hot, humid air comes in contact with the evaporator, and it condenses all of the water vapor out to leave you with a bucket of water, and the heat that's been extracted from that hot, humid air then simply reheats the air to go through the cycle again, removing more water vapor. So the best heat pump clothes dryers on the market are around 10 or even 11 star ratings, and they are about 4 times as efficient as a normal clothes dryer. So this is a simple example, which is producing a bucket of water and dry clothes from a whole lot of clothes that were wet. And that's basically the same as the heat pump is doing with the exhaust air from the aquatic centre. Now, I'm conscious time's moving on, so I'll be fairly quick here. But again, one of the interesting things is that the heat flows in an aquatic centre and the energy flows are actually quite complex. And this diagram here just gives you one example of a sort of a breakdown of the proportions. And you can see that the yellow part is heating the pool water. The pale blue part is the energy that's used to ventilate and heat and cool the pool hall. And there's a lot of that. And then there's other appliances and equipment and things like that. So the thing is that all of these things are interwoven. So for example, a lot of the heat that is heating the building is coming from the water that is evaporating into the pool hall. Likewise, the lights in the building are providing heat that is also heating not just the pool hall, but other rooms. So there's all these kinds of things going on. And I think historically we haven't really understood just how complicated all of this is. And hence we haven't realized how much potential there is to scavenge heat energy from different places to get it into the pool. So we need to buy less energy. So this is just pointing out that there's a whole range of other things going on beyond just heating the pool water. But one of the key things that's important is that the temperature and the amount of heating and cooling energy needed for the pool hall is very sensitive to the building itself, the thermal performance and the ventilation rate of the building. And to be honest, most aquatic centres are appallingly bad in terms of their thermal performance. I mean, they certainly wouldn't pass the house energy rating standards. And again, one of the points I made earlier is that in fact, you can get a bonus with a heat pump because it's got a hot side and a cold side. You can use the cold side to help cool parts of the building and the pool hall, and you can get heating and cooling at the same time from these devices. Okay, this is my last slide. I just wanted to highlight the issue of glazing because a lot of pools have a lot of glazing, including roof glazing, and the glazing is an enormous problem. Solar radiation can come through the glazing, and in summer, that means that you can be putting in hundreds of watts of heat through every square metre of glass that's exposed to sun. So it's like having a bank of electric radiators heating a place that's already hot. And of course, you get all the conduction and things like that going on. And so one of the things that's really important to realise is that even the most advanced glazing systems we have are not very good insulators compared with an insulated wall. So this just shows you a range of glazing options, and I couldn't fit the thermal resistance of the wall on this scale because it's up at 2 and the scale here is only going to 0.5. So you can see that a single glazed wall in a pool that's got air movement over the surface of the indoor surface of the pool is a pathetically poor insulator, to put it bluntly. And in fact, what you'll find is that you'll get a lot of condensation on those walls. And when that water vapor is condensing on the walls, enormous amounts of heat are being fed into the glass, which is then escaping to the outside. So it's incredibly important to get a really good building. And unfortunately, this is something that is a very, very rare thing in Australia. So I'll finish at that point, and I hope that's a useful contribution.
Thanks so much, Alan. I think you gave us a great overview about, sort of moving heat away from areas where it's not useful to areas where it can be useful, and also that heat pumps obviously work in cold temperatures, which is a new benchmark when you're comparing cold to deep space. I think Canberra is now considered tropical versus deep space, so that's excellent. And of course, you walked through sort of how if you can tap that wasted heat, there's a lot of benefits, from heating and cooling, ventilating, and all sorts of things. But heat pumps aren't the only option available. You drew, particularly at the last slide, attention to other areas of the centre to look at, such as insulation, and making sure that you're looking at the project holistically for energy savings and emission savings, which is fantastic. So I'd now like to introduce Amna Abdalla, Sustainability Engineer for the Yarra City Council. Amna was the project sponsor for the Yarra City Council's heat pump technical evaluation for the Richmond Recreation Centre, which in terms of wet areas includes a 50-metre indoor pool, a learn-to-swim pool, a toddler pool, a spa, sauna, steam room, so plenty of hot humid air, as Alan was talking about. Amna has worked for Carbonetics, and I hope I pronounced that correctly, as a sustainability engineer, and for Marriott International as their coordinator of assets and energy management. Welcome, Amna. I think you're on mute.
Sorry. Thank you, Kylie. Yeah, so thank you everyone for joining us today. And yes, as Kylie said, my name is Amna and I'm the Sustainable Energy Officer at City of Yarra in Victoria. And I'm here to just share some of our work around going off gas and particularly around electrifying and going off gas for aquatic centers. So City of Yarra, for those who don't know, is a small inner city council in Victoria. It's comprised of a very diverse population of around 100,000 residents and over 16,000 businesses, mostly small and independent businesses. We have a long history of climate action. We have been a certified carbon neutral organization since 2012, first in Victoria and only second in all of Australia after the city of Sydney. And since 2008, we have achieved more than 55% reduction on our gas emissions, specifically from electricity through energy efficiency upgrades and energy performance contracts. So that was up until 2018. Beginning of 2019, we started sourcing renewable electricity, which furthered our greenhouse gas emissions reduction to a whopping 72%. And from that point on, we started, focusing on our natural gas emissions. So, as I said, the sourcing of renewable electricity was kind of the trigger point for us to look into our gas, natural gas emissions. So we are signatories to the Melbourne Renewable Energy Project Power Purchase Agreement, which started in early 2019. And from there, natural gas has become the largest source of direct emissions in our council operations. So as you can see in the graph, around 45% of our emissions are from gas. Transport is still slightly bigger, but a lot of it is indirect through our contractors and fleet, and that is being dealt with as well. But it seemed like going off gas would be the next thing, the next natural step at this stage for the organization. The second sort of like milestone that really triggered this initiative for us is the adoption of our climate emergency plan in this year, and with commitments to basically phase out all of council buildings, majority of council buildings of gas by 2022, and that is around 30 sites out of 38, and for all of council buildings to be zero carbon operation before 2030. So from there on, we started to understand what is our gas consumption, where are we using gas and what for, to basically look into electrical alternatives. So we realized that we have a total of 38 gas using facilities, and we broke them down to 3 categories. First one is what we classified as simple buildings, and they're simple in terms of their gas appliances or gas using equipment. So there would be sort of like residential scale hot water systems or gas cooktops, and those centers are like such as childcare centers, sports pavilions, etc. And there are about 30 sites, and with the right resources and planning, we could phase them out of gas in the next 2 years. Then we have complex buildings, and they're complex buildings because of the the type of gas using equipment in there, which is mostly centralized HVAC systems using a combination of a chiller and a boiler, and they're more complex because of a boiler has a bigger heating output, so we need to figure out what would be the suitable electric alternative to that. And because these systems are more integrated into the building, so changing them would require more modifications and funds as well. And the third one was aquatic centers. We operate 3 aquatic centers, and as you can see in the graph, close to 80% of our gas use is to those aquatic centers, and mainly for heating, but also for electricity generation through 3 cogeneration systems. So we decided, following the 80-20 rule, we would start with aquatic centers and figure out how we are going to electrify them, to tackle the majority of our gas emissions. But then we faced a problem. The problem was that there was very conflicting advice from consultants and in the industry around what we can do with aquatic centers and whether it's even possible to electrify them. We did our own research, and heat pumps were the only logical solution, and it's proven overseas, and it's been operating aquatic centers, district heating, all sorts of heating applications in much colder climates for decades. But for some reason they are surrounded by misinformation and unjustified risk perception in Victoria, or around us. So we decided to do something because we were very convinced that this is the way to go, but it's just nothing was cooperating to help us go that direction. So we decided to conduct a peer-reviewed study to support better understanding of the technology. And the reason we wanted to do that is to basically change the conversation from whether it's possible to electrify a leisure center, an aquatic center, whether heat pumps are viable or not, and will they work in our climate or not, which is considered cooler than states like Queensland, where heat pumps are more common, to no, they are viable, they work, let's figure out how we can get them in. So we did that using, working with a consortium of energy consultants, refrigeration engineers, and a system manufacturer. The study was led and designed and reviewed and everything by us. And then we had it peer reviewed by some industry experts, including Pears, who's with us today. So, and after that, we shared this study with both councils and consultants and everyone who was interested to read it, really, to just trigger a perception change around how we look at this technology and how we tackle this problem. So the approach we took when we started the study is we needed to choose sort of like a heat pump system to evaluate its feasibility for an aquatic center, one of ours. And from the beginning, we had, because there are many options, many heat pump options, and the major difference being the refrigerant. So we had a choice, and the main choice was whether to go for a natural or synthetic refrigerant. And we thought while we're doing this, and this is for the purpose of feasibility and analysis, if we had our way and we did it right, because this whole movement is triggered by emissions reduction and climate action. If we were doing it right, we would use a natural refrigerant from the get-go. So for that purpose only, we didn't look at synthetic refrigerant. That being said, at this stage, I think there are still heat pumps systems equipped with synthetic refrigerants that would be suitable to certain applications, and that's still fine. It doesn't take from the win of electrification, because I feel at this stage fighting the battle of going off gas is much bigger than fighting the battle of phasing down synthetic refrigerant. And once you use an electric alternatives, even with the synthetic refrigerants down the line, when at the end of life cycle or something, you can just replace that system with a system equipped with a natural refrigerant, and it will be a plug and play because you already have the infrastructure and everything ready to go. But for the purposes of this study, we decided to evaluate something with a natural refrigerant, and we had two choices: either carbon dioxide with a global warming potential of 1, or ammonia with a global warming potential of 0. Then we started looking into both of these options, first being carbon dioxide. So, what we found out that they are generally small in capacity. So for the massive heat demands of an aquatic center, we would need a bank of 5-10 pumps or even more, or you would need to use a gas backup for, like during big demand days or seasons. They have an average COP of 4.2, which is reasonable. But the reason we decided to rule them out, and we decided that they are not really the most suitable for an aquatic application, is because for carbon dioxide as a refrigerant, it has a critical temperature of 31 degrees. And what that means is that around this range of temperature, 30, 31, 32 degrees, the gas doesn't condensate during the refrigeration cycle, just like Alan explained. And if it doesn't condensate, that affects the efficiency of the system. And the main reason for an aquatic, why it's not suitable for an aquatic environment, is that 30 degrees or 28 degrees or that range would be the return water from the pool, the temperature range for a return water, which would be the inlet to the system. So yes, it won't be ideal for pool heating, but that being said, it's usually perfect for domestic hot water applications, because the carbon dioxide is more efficient the bigger the temperature difference between the inlet and outlet, and that would be, again, ideal for domestic hot water, where you would need water temperatures of 60 degrees plus. Then we looked at the ammonia heat pumps, and we found that they have industrial scale capacities up to 2,000 kilowatts of heat output, average COP of 6, so they are extremely efficient, probably one of the most efficient refrigerant out there, and they could achieve a combined COP of which is the coefficient of performance, as Alan explained, of 11 if you are using both the cooling and heating sides of the system. It can produce water up to 80 degrees or heat up to 80 degrees, and widely used as a refrigerant in the refrigeration industry, including here in Australia. So it wasn't something new. It was new in the sense that it hasn't been really used a lot ever in aquatic centers or in space heating, just a few applications here and there in Australia, but they are heavily used as in the refrigeration industry. So there is local experience and knowledge available, just in a different industry, in the refrigeration industry, not in the building services industry, where we are currently working. So we decided to use that for the study and demonstrate its feasibility for aquatic centers, particularly showcasing its seasonal COP, because the performance coefficient of performance changes with ambient temperature, and that's why we always hear that argument of, are they viable in cooler climates, or are they viable in Victoria? But that's exactly what we wanted to showcase, is that yes, even on the coldest day and hour, here there is still plenty of heat for the heat pump to use. So we wanted to show that. We wanted to use only air as a heat source. So that was sort of like a worst case scenario. So probably when we go into the project and actually electrify our aquatic center, we will probably use heat recovery from pool hall air exhaust, maybe tap into wastewater mains if we can. So we will try to use more heat sources as possible to improve the efficiency. But for the purposes of the study, we wanted to just do a worst case scenario modeling to show that, you know, the absolute worst case with just ambient air, cold ambient air in the winter, you still have enough, we will still have enough energy to cover our peak demand, which is also in winter. We sized the system for peak demand, so no gas backup at all. And we, for the heat load or for the heat demand, we used hourly data from our Richmond Aquatic Center, which is pictured here. So as you can see, it has a humongous pool hall. It used to actually be an airplane hangar. It's very leaky and old and a lot of glazing. So that we are definitely using more heat than we need to, but that's currently what we have. And because of you know, multiple energy efficiency projects and energy performance contracts a few years ago, we ended up having extensive submetering infrastructure in the building, covering every aspect. So we have submetering on the HVAC, on the heating, on gas, on water, on everything. And from there, we were able to build, you know, a very, like a real profile of what kind of the energy levels that we are using for our building, and test whether we can meet that demand using a heat pump. So that's where we started the technical evaluations using ammonia heat pumps for Richmond Aquatic Centers. And we got to designing a system using 2 heat pumps and using heating hot water and chilled water loops. So it was an integrated or a centralized system for the whole site, and it will serve both the pool hall, HVAC, and domestic hot water. So for the heating load, we calculated the heating load needed for pool heating, pool hall heating, space heating for the rest of the center, everywhere that is air conditioned, and the domestic hot water load. Then for the cooling load, it was cooling for air conditioned spaces, but also pool hall when needed. And as Alan explained earlier, you know, although we need to heat our pool hall most of the year here, we do have those days when the outside air temperature exceeds 28-30 degrees, which is, you know, the ideal temperatures for a pool hall environment. And that's when we completely lose climate control in the pool hall. We start having evaporation, condensation, corrosion on the structure, everything, because, you know, it's really hot in there and it's really humid and there's nothing we can do. So that's why if we have excess cooling, free cooling essentially, and if we can cool down the pool hall back to 28 degrees, the desired temperature, and, you know, dehumidify as well, that would be an amazing outcome from having such a system. So having all of that, we also compiled the hourly ambient temperatures for our Richmond location all year round and matched them with the corresponding COP from the system. So for every ambient temperature hourly, we matched the corresponding COP from the system. And this is what we came up with. So the red graph, the red line at the bottom is our heating load. And as I said, that is pool heating, pool hall heating, and space heating all year round. And we can see that our peak is sort of around 800 kilowatts in the winter. And this is the heat output, maximum heat output from the system to at ambient temperature. So this is using ambient air as a heat source only at ambient temperature all year round. And this is based on hourly data. For the graph, we plotted a daily average just to reduce the number of points, but it's based on hourly data. So you can see how the heating output from the system drops in winter, almost sort of like by a third or something, but still, even at its lowest, we still had plenty to cover our peak demand. And honestly, although the system we didn't size, like the system sizes were reasonable, I totally think we can even size down, especially if we improve the efficiency of the system using multiple heat sources. Also, from the findings, we plotted our heating demand. So this is our heating demand all year round. Again, it's an average here. And if the system worked to only meet this heating demand, this is the equivalent cooling, because the system, like we use the heat, but we have the cooling side of the system, because it extracts the heat from air. So we end up having cool air on the side. So this is the equivalent cooling that we would get from the system all year round. And at the bottom, this is our actual cooling demand. So although we have multiple gym facilities and group fitness rooms, creche offices, everything, this is how much cooling we need currently. So all of this additional cooling, and including here in the summer months, can be utilized to cool the pool hall, can be utilized to even, cool a nearby building. If you have like a nearby council building, you can extend chilled water pipes, maybe an ice rink if you have one. Like, the options are limitless, and this is absolutely free at this stage, like, because you're only paying to produce this. And these are the seasonal COPs, here for heating and here for cooling. And this is the interesting thing. Although ammonia is conventionally used as a refrigerant in the refrigeration industry, it's actually more efficient in heating application than it is in cooling applications. Like you can see, it's very efficient as, for refrigeration, but it's much more efficient for heating. So findings based on our test on our current energy use on Richmond Recreation Center, we found that the specific energy consumption, which is basically kilowatt hours used per meter cube per annum, and that's sort of like an energy intensity for volume, was reduced by 76%. And the reason for that is that because we're using heating and cooling from the same system, using the same energy, like the same kilowatt hour we're using produces both heating and cooling. And that's just, amazing in terms of efficiency and optimization. We achieved cost savings of 36%, and that is using our current sort of like spend in both energy costs and maintenance costs. And the maintenance cost savings were significant because currently we have a decentralized HVAC system, and we service all of that. We service our boilers, we service our cogeneration systems, we service our, again, decentralized domestic hot water system. We have, I think, about 8 or 9 hot water systems in there, where with this system, we would be only serving 2 heat pumps. That's it, with like yearly maintenance contract. And also realized, just how many opportunities for optimizations there is for such a system compared to a conventional gas system. The more solar we can fit on the roof, the better, like the efficiency outcomes are, because it will be all absorbed on site. We can utilize the free cooling, as I said. We can use heat recovery from the pool hall exhaust air, or even gray water from our own waste lines. And we can also use thermal storage, sort of like for demand, demand control, or like load shifting at night or something like that. So yes, like the opportunities are endless for optimization with such a system. And also generally for just our going off gas journey so far, because this study also applicable to buildings as well, because while it's a different application, it's sort of the same thing. It's those heat pumps will work as an alternative for boilers. And yeah, we have been doing the same with our complex buildings, as I said earlier. So some of the things we realized so far is that knowledge sharing and collaboration between councils is key to support this transition. And that's why, we were very keen to share our report. We participate in such webinars and all of that, because, the more the industry is definitely not on our side here, or at least they're not ready yet. If we can help shift them or trigger this, new direction, it will make it easier for all of us, and like for the whole nation as well. And when we come together about this and share our knowledge and just support each other, it will further that more. And honestly, at this stage, it just takes 1 or 2 councils to actually get this done. And it might be easier for another councils where they're building a new center or they have a plant redevelopment or whatever, and then it can then be used as the example. We don't need to talk about centers or applications in Europe. We can talk about one here in Victoria or in New South Wales or somewhere closer. The building services industry is definitely very reliant on gas, and they're very reluctant and hesitant to explore alternatives. And that's why we found us being the customer, being more informed would help push it and push them and direct them to that direction to explore and like just get comfortable with new technologies, or not new technologies, just different technologies to what they're used to.
Thanks, Amna. Fantastic, much appreciated. I'm sure you'll get lots of questions at the Q&A session.
Yes.
But I'd like to introduce Ros Kingston, Senior Sustainability Officer from Brimbank City Council. Geez, I'm having trouble with my words today, sorry. Ross and his team are working on a 100% renewable energy powered leisure centre underpinned by heat pumps coupled with thermal storage and solar PV. The project will be part of the redevelopment of the St Albans Leisure Centre beginning in November 2020. So I'm sure we'll get an update any second now. The redevelopment will include not only a 10-lane, 50-metre pool, but also 2 large water slides and various learn to swim areas, spas and more. Welcome, Ross.
Thanks, Kylie, and and thanks everyone for attending. It's great to see so many people tuning in to learn about all these great developments, because there's a lot of work to do in the aquatic centre space, and it has really great implications for the wider building industry itself. I'm presenting from Bunurong land down in Victoria, in Melbourne, and just want to pay my respects to the traditional owners of the land I live and work on, and the elders, and just draw the connection. We're talking energy efficiency aside, that we're, in a nutshell, we're trying to move away from the fossil fuel world that we've inhabited for the last 100 years, which itself is caught up in an extractive colonial project, and there's still many battles being waged on sovereign traditional lands in Australia relating to new gas fields being sought to be opened up. I can think of a couple in the Beetaloo Basin, the Narrabri gas project being sought by Santos. All these projects are in one way or other opposed by the traditional owners of those lands, not to mention the Adani battle that is still going on in Queensland. I just want to acknowledge that those issues are still occurring, and that should be a big part of the conversation that we're talking about. That's not to say renewable energy projects should also need to seek endorsement from traditional owners on the lands which they're taking place, but it's just particularly acute with fossil fuel extraction projects. The St Albans Leisure Centre project is a redevelopment of the St Albans Leisure Centre, and we in 2019, so where the project Amna's describing was a retrofit. This is I guess a new aquatic centre, and we adopted our climate emergency plan in 2019, like many other councils around the country, and based on that really strong position that our council was really good to have put out, it's just not realistic for us to continue on our biggest capital works project that we'll probably ever deliver. Really, it's a really expensive project that we would be rebuilding that based on fossil fuel technology. So we set out to create a zero emissions facility, and as Amna was describing, similar to what Amna was describing, at Yarra, we were convinced that an all-electric facility was the way to do that, coupled with a large solar system. And like Yarra will soon be on a 100% renewable electricity supply. So with those two, rooftop solar and off-site renewable electricity supply, that was the kind of pathway to a zero emissions centre that we saw. And we set about trying to design that. And sorry, a lot of this is going to be reiterating the experience Amna has been through. But what we encountered is an industry that's thoroughly not equipped to provide those solutions to the local government industry. And so it's projects like this and the one that Amna is trying to drive at Yarra and others around the country that will try to tip the balance. And unfortunately, we're at this stage where we have to drive it from the council side of things rather than the building industry, which is just not particularly innovative at the moment. So for those seeking to do the same, I would just say, if you ever get an engineer or a builder or an architect that tries to tell you this isn't possible, just tell them it's rubbish, that this is happening, this is the way to go, and that arm yourself with some good technical expertise to provide that backup, but that is available, and I can definitely help anyone out, give people some direction on that if they're needing those kind of resources. So that was our climate emergency plan. So we had the strategic direction, and that was pretty important actually, because it's been a really rocky road to get to where we are now, which is we've got all the funding approved, and the design is just being completed as we speak. And yeah, it's all happening. That St Albans Leisure Centre is getting rebuilt over the next year or so, and will be operational in 2022. And at that stage, everyone can come and have a look at a 100% renewable energy powered aquatic centre, which we're not 100% sure, but we think might be the first in Australia to achieve that, because there is just the trilogy of having the all electric system with the renewable electricity PPA is the way that that's being achieved, and that's only a recent development. These were just the pros and cons we ran through to, I guess, convince, and there were quite a few different audiences we had to convince that this was going to be a viable opportunity. Firstly, in the pros for the electric heat pump system was the fact that it was central to our climate change strategy. We simply couldn't get to zero emissions without going down this path. There are, of course, carbon offsets, but it's well beyond time that we actually just start shifting the technology, and that was the way we wanted to go. We've done the business case, and it's still this is a whole area of conversation. There are whole of life cost benefits, but at this stage we're finding on a greenfield kind of aquatic centre project, it's difficult to get the upfront costs into that sort of, under 10-year payback that a lot of sustainability practitioners and councils would like to generally looking for on the energy efficiency projects. But I might return to that in a little bit in this presentation. Gas prices, the days of cheap gas are long gone, and they're volatile, and there's no way to kind of understand where they'll go in the future. With the renewable electricity PPAs, we have a partially fixed price, and we get some budget certainty around what our ongoing costs for electricity will be. And we can also, with the electricity, you've always got the opportunity to go even bigger with your solar PV system. This project's going to have a 500 kilowatt solar PV system on site, and but we've done solar car parks in the past as well, and so we can always increase that solar if we wish, but we've got 500 kilowatts to begin with. And we're also seeing aquatic centres in as a climate change adaptation thing as areas where, you know, we're getting, as people following the data, or just anyone on the street can know that our summers are being hit with more and more extreme heat waves. And aquatic centres can be a place of refuge, but if they're powered by fossil fuels and they're, you know, energy guzzling machines, then that's kind of like a maladaptation. So we're wanting to see these places as places the community can come and seek refuge from heat waves and extreme heat during summer, but we need to do that with 100% renewable electricity, otherwise we're just adding to the problem. And on the probably the only good thing about to say about what we call the business as usual approach for aquatic centres is, yeah, you might be able to achieve a lower upfront cost, but that will steadily be, even that will steadily be no longer true as this new design shift occurs over the coming years. Next slide, please, Julie. Thank you. I think this has probably been covered off. The way an integrated heat pump system works is probably being covered off enough in Amna and Alan's presentation, so I won't dwell on this. But we were our original intention with the heat pump design was to do the pull hole air exhaust heat recovery, feeding back into the heat pump system. We're not going to be doing that in this instance, largely for commercial reasons. We hit road bumps, hit a bit turbulence during the procurement phase, and had to change the heat pump type technology. We were going with the ammonia heat pumps, but we've now got the what's called a HFO heat pump, which has the refrigerant issue that Amna mentioned, and yeah, that caused some issues. But we do, Alan mentioned the typical approach for air handling units is to have heat recovery anyway, which we've still got that. So we still are recovering the heat, but just not integrating it into the heat pump system. So yeah, definitely advocate anyone else looking to go in this path, really fight for that opportunity, because it is a really big opportunity. But yeah, that's probably the only thing to mention there. Next slide, please. I'll probably skip this. That's just around the cold temperature. That's just that misinformation issue that's out there around heat pumps in cold climates, and I think we've pretty much addressed that. Next slide, please. The business case. So on this particular project, where we actually had, when we set out at the beginning of this process, there was all that misperception around the suitability of heat pumps and the viability. And so as much as we wanted to achieve zero emissions, the design team that had been actually put together for this project just went full steam ahead on the business as usual design. And so we were on this particular process, we've got a really good, clear comparison between what the business as usual design was going to cost and what the pathway we've actually ended up going down has costed. And it's costed council about $700, close to $800,000 extra than the business as usual design was going to cost. And we have attracted funding as well, because it's like an innovation project. But in a nutshell, what I would say about that is and I'm happy to anyone else to get in touch with me, and I can go through the fine detail of the cost breakdown of what's involved in this undertaking. In a year or two, a heat pump based, 100% renewable energy powered aquatic centre should not come at a capital premium compared to a business as usual design. We've copped a lot of costs from just, we actually ended up having to get this system procured as a variation to the actual building contract. So typically, you'd do your design and you'd go and tender that. But because of the industry recalcitrance, basically, and we were having to push this option all the way, we ended up in a situation where we had to request a variation to the building contract. and that's not a situation you want to be in. You lose all your procurement kind of position, and so in a nutshell, we've copped a lot of additional costs simply through that commercial pitfall. And once this becomes the business as usual approach, I cannot foresee any reason why this heat pump based aquatic centres should be any more expensive to build than a normal aquatic centre. So don't be discouraged by cost situations, but make sure that if you are setting out on an aquatic centre rebuild or a new aquatic centre, make sure that it's absolutely crystal clear that it is to be a fossil fuel free facility, and that the design team being put together for that project needs to have demonstrated experience on electrified facilities, and you'll probably you'll be in a good stead to have a good outcome. So yeah, I mean, this is probably a first of, or a first among, a handful of innovation projects taking place in this space. So yeah, there were some additional, there is a cost premium for it, but hopefully through the work ourselves and Amna and others are doing, where this is going to become business as usual, and it's going to be a lot more smoother path for other councils to follow.
Excellent. Thanks very much, Ross. We might open it up to questions. I have seen that there's probably two from Rob Twiddle. I'll take the first one, which anyone's welcome to answer, but I suspect it might be one for yourself, Alan. What is the expected lifespan of heat pumps, as environmental factors can make these only viable for 10 to 15 years?
Well, a well-designed and well-maintained heat pump can last for a very long time. And if you did want to switch it over to something else, then it would have some asset value if you were switching. Keep in mind that a heat pump is not much different from a commercial building chiller, and we have thousands of buildings with big chillers in them around Australia. As Amna said, this is not rocket science. This is normal approach to things in other countries. So I don't think that's a long-term issue, really.
And I'm assuming with, I think Amna's presentation pointed out sort of 36% cost savings. So, you've got a bit of wriggle room to replace units if you need to. So that sounds like heat pumps are still a very go-to solution here. Amna or Ross, did you want to jump in on that at all?
Yes, just on the life cycle one, it depends. If you're talking about the small scale heat pumps for like domestic hot water, yes, it's around 10 to 15 years. But if we are talking large scale heat pump chillers, it's actually 20 to 30 years. And, the more large scale or industrial scale you go, like the ammonia heat pumps are actually made from special alloys and stuff. So even the highly corrosive environment for aquatic centers doesn't affect that. So yeah, definitely at least double of that life cycle, especially if well maintained.
And that's fantastic, because I think in your presentation, Amna, you also noted that the ammonia ones are well used in sort of, I guess, supermarkets and places like that, but not so common in aquatic centres, but clearly are very extremely efficient and are a great option, particularly with such a long life. Particularly as they are a natural refrigerant rather than a synthetic refrigerant. So that's fantastic. Rob had another one, which I'm not sure who's technically placed to best answer it, but I'll just read it out. How do you go with contaminants like chloramines being used as co-heating and affecting the lifespan of the product, as it is highly reactive to metals?
Yeah. Sorry.
I think I'm
that one.
Yeah, I can talk. I'm not an aquatic centre engineer, and it's probably best to speak to someone you know, a building services engineer that has a lot of experience in this space. But yeah, it is an issue. It depends on with that harvesting of the pool hall water vapor. My understanding, it can be an issue if you're recirculating that, but there's different options to go around, like suppressing the chloramines in the air. And while we're not harvesting the water vapor to reintegrate into the heat pump system, we've actually got a what's called a air pressurization optimization system, which actually just sort of suppresses humidity in the pool hall itself and just keeps humidity down over the long term. But yeah, look, that's a pretty technical question, but it's an issue faced by all aquatic centres, and there are solutions. It's sort of somewhat separate from the gas or heat pump question.
Yeah, and also just like what we do with gas boilers now, we can have sort of like an offset, so we don't have the cross contamination with chlorum, you know, like treated water to the water running through the system, and that could just simply be by the use of heat exchangers in between, so the heat pump or even the boiler don't actually, you know, directly interact with treated water. So that's simple as that. And again, you know, there are special systems that can also withstand those corrosive elements if, you know, specified properly.
Yeah, that's right. There's no reason to expose the actual mechanical plant to those, but I think there can be issues, just the way you're wanting to kind of recycle your pool hall air. Some heat recovery, and this isn't actually related to heat pumps, but some heat recovery solutions actually recirculate the air and don't actually take the chloramines out of it. So that would be an issue, both for the facility itself, but also for human just health, because they're a bit nasty. And so, but there are solutions where you can actually recover the heat from the air and use it for either heat recovery or to actually boost the heat pump efficiency that actually do away with the chloramines, and also you gain that really great heat recovery. But for a more detailed explanation, please go to someone with a lot more technical expertise than myself. Yeah.
Thanks, guys. Next to around outdoor pools. So we spent a lot of time obviously talking about indoor pools, and so there's a couple of questions here which I'll just read out in relation to outdoor pools. The first one is, are heat pumps an effective option for outdoor pools? We have 2 outdoor aquatic centres and are looking at heat pumps for both sites. One will potentially require a power upgrade with Ausgrid. Another site is more simple. We are based in Sydney. So who wants to take that key question, which is, are heat pumps an effective option for outdoor pools? Alan, you just put your hand up. Off you go.
Yeah. Well, the thing to keep in mind is that most outdoor pools are heated in the warmer part of the year. And as such, the heat pump is more efficient when it's heating across a smaller temperature differential. So you need to be a bit careful about just how you're doing your calculations, or, you know, maybe you might allow a little bit more variation in pool temperature. Certainly, the heat pump, personally, my view is that the capacity to recover both the latent heat from condensing exhaust air, water in exhaust air and the exhaust air is actually a very big issue. And I have to admit, I'm a little concerned that Brimbank are not pushing that as hard as I would like to see. And obviously with an outdoor pool, you can't do that. But that's where you come back to an outdoor pool. There's a few key things. One is they're very sensitive to wind speed. So when you're designing it, you need to protect it as much as you can from the wind. You also need to make it as easy as possible and utilise pool blanket or equivalent as much as possible to minimise all of your requirements for energy. So, and likewise not try and heat it too much. So they're all the things to do first. Second, the thing is that using a heat pump, again, this is where battery technology will start to play out as well, because basically summer is when you've got really high solar output from a rooftop solar system. And if you can combine that with some energy storage, and it could be thermal storage as well as battery storage, and if you can minimize the losses from the pool, you can start to get quite an efficient system. And one of the things, again, through the summer is that if you're looking at buying in power, the cost of solar power is likely to be quite low around the middle of sunny days, right into spring and autumn, in which case you can be buying your power with the right contract at a very low price. So for all those kinds of reasons, I think that the heat pump is looking pretty good for an outdoor pool. But you really, again, look, you need to be careful, and you need to try to combine extreme efficiency, management of the storage approaches and things like that with the heat pump.
I think I've heard along the grapevine that Glen Ira Council in Melbourne is building a outdoor pool facility that is going to be run on heat pumps. So they might be someone that you'd be interested to get in touch with.
I'm fairly sure it's been done at quite a few pools, outdoor pools already in Sydney. I'm fairly sure the old Parramatta pool was running on a heat pump system there. And the only consideration, I think, performance-wise, was that 5 days a year they hadn't allowed for it operating below 5 degrees or so ambient temperature, and that was having some icing issues and some performance. So if that's fully belts and braces design, you'd have a defrost system, just like you do with your freezer, to make sure that you're allowed for those half a dozen days a year that you can still get the right heating that you need when it's very cold.
The other thing too is there may be useful heat sources nearby, like if you happen to have a supermarket with a big refrigeration system providing a lot of waste heat, or even a sewer or a water main or a nearby lake. All of those are potential heat sources that could overcome the problem of the low temperatures at some times.
Yep. Data center as well is another option. Yep. Next to one of those, but most likely, it's going to be something like a shopping center or the likes, a refrigeration plant that is also rejecting heat in those winter months.
And again, in lots of areas in Europe, there's opportunities to look at how those communities are actually working in tandem in an integrated way to actually share their heating and their cooling, so to speak, rather than operating in isolated developments. We've got some more questions. Let me just look at them. Someone's saying, to your point about a lake, Alan, someone's saying, yes, there's a Sydney Harbour next to there. So they have a rather large lake.
You only want to use it when it's warmer than the ambient air. Otherwise, use the ambient air because the compressor will be more efficient. So if it's a 30-degree day, use the heat pump with ambient energy, not the Sydney Harbour, unless it's really warm in Sydney Harbour. I haven't swum there.
It's nice. About 19 degrees, Alan. It'd be perfect for a heat pump. They, especially in winter, maybe it gets down to 17 at the worst, but absolutely ideal to drive a heat pump.
And we also have Maurice Eames online, who has actually commented to your point, Jared, that oops, now I've lost the comments coming in too fast. I've now lost them. But yes, correct. The Parramatta pool and the Granville pool operate on heat pumps, icing up for a small period, and that was an issue. He was manager of both for 5 years. So if anyone wants to ask about this, Maurice Eames, well, I'm sure he'd be delighted to have a chat. Likewise, Ian Garrard has pointed out that North Sydney Pool has been running on heat pumps for about 20 years with gas backup. They found the cost of operation was much cheaper and lower emissions when using the heat pumps. In fact, about 50% cheaper. So that's putting a challenge to you, Amna, at 36%.
Actually, we looked at case studies from the North Sydney Aquatic Centre when we were doing ours and, reasoning why it's viable. So yeah, I believe you. I saw that.
Well, ladies and gentlemen, before I pass to Tanya for some wrap-up comments, I thought I might just go around to each panelist and just ask what their key messages that they'd like to leave with the audience today in terms of the topic we've had today, which is all about, you know, making aquatic centres much more energy efficient and lower costs and lower emissions. So, Alan, we might start with you. Your key message for everybody.
Well, I think seriously, look very carefully at capturing as much energy from that exhaust air as you can, because if you have a perfect building, all of the heat you're putting into your pool is going out through that hot, moist exhaust air. So you should be able to run on very little energy if you capture it efficiently. I think the other quick one, as others have said, is be very careful who you choose to work with.
Well, that's life in general, though, isn't it? But yes, Amna, to you.
Yes, I would say, just like as a client, be as informed as possible, because there is definitely very dodgy advice around. And yeah, if you know that, doing so, you can just filter out the advice and therefore choose the right, you know, people to work with.
And Ross?
Yeah, just a similar one, really. I mean, hopefully we've convinced you that all electric aquatic centres, all electric high efficiency aquatic centres are a no-brainer. And that's what you should be looking to do on your aquatic centre renewal or new aquatic centre retrofits. Just where we went wrong, we somehow got back to a position where we wanted to be, but where we probably went wrong at the beginning was to just specify a 6-star Green Star project and think that all the great people would just come and coalesce around that and deliver that. That wasn't enough. If you want to set on this pathway, be very clear in your design brief that you want a fossil fuel free facility, and even into details such as the refrigerant and issues like that. It's probably not enough even just to say I want a heat pump based facility. You know, you want a zero emissions facility with a zero global warming potential refrigerant, and you want it to be an integrated system that incorporates all the energy efficiency goodies that are available.
Fantastic. And don't forget that there are, you know, brave councils like Amna's and Ross's that are doing this already, and many others that we heard in the chat and Q&A. So reach out. The RDA is there to help, as well as the councils, to help spread the word, and so is A2EP, and so is local government procurement, which is a fantastic segue for me to quickly introduce Tanya for our closing remarks. So it's my pleasure to hand over to Tanya Lawler, who's from Local Government Procurement. She is a sustainable procurement consultant, assisting councils to integrate sustainability into their procurement processes, and was a member of the Australian Committee for the Development of the ISO 2400 Sustainable Procurement Guidance Standard. Tanya works with local government procurement, and they provide a fully integrated procurement service, including contract panels, consulting, professional development and contract management, predominantly for New South Wales councils. So she's here to help. Over to you, Tanya.
Thank you, Kylie. Just before I start, I think, Jared, did you want to say something?
Oh, sure. Thanks.
Yeah.
Tanya. Sorry to interrupt then. I just wanted, just from an A2EP perspective there as well, we do see this potential of changing to heat pumps away from gas as one of the biggest potentials for CO2 savings for Australia. If every aquatic centre changed. So it is not a small amount. The calculations are above 100,000 tonnes per annum of CO2. This is not easily found around Australia, that quantity of savings. It's really quite unusual to be able to find something like this. So this is why A2EP is quite passionate about trying to help with some change here. We do know the electricity prices are coming down. We do know that gas prices are becoming more uncertain and have trouble. We're going to be meeting renewable electricity prices. We know that ARENA wants to help and back such projects and provide funding, so that we do see mill projects going ahead with the final issue of the designers. Now, to come in a bit of a defense of designers, I think we understand that for the last 10 or 20 years, they've been telling you that you need to use gas with combined heat and power. That's the way to go. And they're just having a bit of trouble changing there because they've been living that for so long now. This is the recommendation. You need to use a gas engine with combined heat and power. So I think within a year or two, they'll see that things can change. They'll get used to the new suppliers. They're used to thinking of dealing with engine manufacturers that do combined heat and power. And now they need to deal with industrial heat pump companies. And that's new. That's new for them as well. But I think over time, you'll see in the next couple of years, you've got that top 5 aquatic centre designers that they'll be changing and they'll get on board. They'll get used to the change. And we just look forward to facilitating and helping them with those changes. We're producing a lot of tools to help with sizing of heat pumps, selecting the right technology, understanding the return on investment. We continue to train them and help them and yourselves. So our door is open to help you with this transition. And we hope this is the first of many such meetings to get this underway. Thanks, Tanya. I'll hand back to you.
No worries. Thanks, Jared. Yeah, and I guess from what Jared just said, the carbon reduction opportunity here is massive, and given that a lot of councils, majority of councils actually across Australia, not just New South Wales, do have very strong carbon reduction targets now and are wanting to take action, climate action as well. Yeah, I thought today was fantastic. I certainly learnt a lot, beginning with Alan about how heat pumps worked. Some great everyday examples. I must admit, when you referred to the refrigerator, that's when it clicked for me. So thank you, Alan. And then 2 really fantastic case studies from Amna and Ross. I think there's some really fantastic learnings there for New South Wales councils, particularly around the process for getting concept acceptance and project approval, because that often seems to be the hurdle for most people. And I'm sure that both Amna and Ross would love to share their learnings more with you. And I think from an LGP perspective and the sustainable choice, we'll look to talk to you more about your case studies and get some information there so that New South Wales Council can readily access that through our website, where they access a lot of the sustainable procurement resources. I think also very important to note out from today is that this is a very energy efficient heating and cooling solution for aquatic centres, but also in general for other buildings too. And when coupled with renewable energy, that's when you get this huge carbon reduction potential and can meet things like net zero emissions targets. Now, in terms of renewable energy, New South Wales councils do have access to a solar PPA arrangement that LGP has and has established in conjunction with the Department of Planning, Industry and Environment. So you can access that through LGP. So that doesn't require any capital outlay, but it does require you purchasing the electricity from that's generated from that system. And it's the asset remains the property of the supplier, but at the end of the PPA contract, the ownership will then convert to the customer, so to the council. We also have an energy services contract where you're able to access energy performance contracting, energy design implementation services, and also efficient lighting, and also the capital purchase of solar panels and batteries. So all of being able to access that through an LGP contract then makes it that much easier from the procurement side of things for you. In terms of, LGP at the moment, we have a sustainability pillar as part of our new strategic plan, which is running for the next 3 years. And that's really heavily backed by the LGP board. So we are looking to do a lot in terms of supporting councils to meet their carbon reduction targets and also to take climate action. But also on the social side of sustainability too, so around social procurement and getting really good social impact from your procurement. And you can contact me about any of that information. But thank you all for coming today and responding to the invitation we sent out. And I'm sure you've found it very valuable. And I hope what you take away from today really helps to enable you to progress your energy savings initiatives in your council's aquatic centres. I think as Therese mentioned earlier, there will be a recording of this webinar along with the slides that will be emailed to you, along with contact details as well. So if you want to get in touch with anyone to further the conversation, then you'll be able to do that. And I think that's it for us today. Kylie or Therese, would you like to say anything else, or shall we sign off?
I think everyone should go and get a mission for an electrified aquatic centre. Make sure that they're talking to the councils, to A2EP, RDA and local government procurement as to how to do it, because it is possible. You can get 36 to 50% cost savings, if not more. And we just need to be a bit smarter about how we engage with the procurement side of things so that we get the right designers and the right equipment. Thanks.
Okay, thank you.
Everyone.
Have a lovely day, everybody.
Thanks, everyone.
Thank you.